going to find the zeros of any polynomial function and then state the multiplicity of those particular functions. To get started with this, we could look at the graph of it, and that would give us kind of a better picture of what the word zeros means. So zeros, and I'll use the word roots as well, basically is the solution to setting p at x equal to 0. So, you know, if p at x is 0, then x minus 5 squared times x plus 2 cubed times x plus 4. Either any of these three chunks could be 0. So if you had a 0 here, you'd have 0 times the rest of it. And 0 times anything, we learned way back when, hopefully, 0 times the number 4, that is 0. So, 0 times 157 is 0. So, same goes here. 0 times anything is 0. So, and it goes for all three of the binomial numbers there, the binomials. So, what we're going to do then is set each binomial equal to 0. And you got to also take into account that x minus 5 squared, well, really there's two of those. It occurs twice. The same number occurs twice in the problem, the same root. This one, there's three of them. X plus 2 is to the third power. So if you expanded this thing out, we're not going to multiply them, but this is what it would look like with each individual root listed out. And so you set these to 0, because any one of these could be 0 and would make the whole function 0. So in our case, x minus 5 could be 0. Well, when you do that, you'd add 5. And so 5 would give you 0 in the function. So you could test that. Well, take the number 5. I'll do it with a different color. Take the number 5 and plug it in here. Well, 5 minus 5 is 0. Well, that makes these both 0, and 0 times anything is 0. So when you multiply that out, it's all 0. So there's one of my roots. Now, it has a multiplicity of 2. I'm going to be a little lazy. Well, because there were 2 of those roots, 2 5s occurred. And that'll be important when we're graphing this later. This number 5 will look a little different than the rest. Also, we've got a group of 3x plus 2's, so we'll set that to 0 to see what its root is. You minus 2 from both sides. And so another one of your roots is negative 2. And then finally you've got that, and its multiplicity, sorry, I almost forgot about that, multiplicity. It has a multiplicity of 3 because it occurs 3 times in the polynomial. And then the last one is x plus 4. Set that to 0. And so x equals negative 4, because you would subtract 4, sorry, not showing my work. And so you have another root of x equals negative 4. So these are the 3 roots, and its multiplicity is 1. It only occurs once. Of 1. Okay? So those are the 3 roots. Now, why do we call them zeros? Because that's what would produce 0 in the function. And it's also your x-intercepts. So it's good to take a look at the graph. So I'll reposition here. And this particular, here's the graph in GeoGebra. And if you look at it, here it is. And I'll kind of make it appear and disappear. There it is. And you can see that if I intersect the function with the x-axis, my roots should appear, and there they all are. So negative 4, 0, negative 2, 0, negative 2, 0, and 5, 0. And notice it lists negative 2, 0 twice, which we know it actually happens 3 times, and 5 occurs twice. So, and let's kind of take a look at the function if we change it, because I think it's of value to see what's happening here. So if you change the y-axis, now you can kind of see where the minimum is, some of your local min and maxes are, some inflection points. Not that we're after any of those in this video. We're just mainly concerned with the roots. But here's just generally what this polynomial looks like if you have a range from 0 up to 4,000, going by thousands. And notice at 5, anywhere there's an multiplicity of an even multiplicity like 2 or 4, your graph is always going to bounce off of the x-axis. If it's an odd multiplicity like our 4 and our negative 4 and our negative 2 was, it passes through the x-axis. And you can see that in both cases for B here and A here. So there's generally what a polynomial graph looks like. That's how we find our zeros. That's what zeros are. They're the x-intercepts if you were to graph the function. And I hope this helps, and I'll see you next time, because I think we've covered everything we need to cover on this one.